In this video, we are going to look at electrical current, and we're going to show you that there's actually two flows happening simultaneously. Um, there is the flow of electrons, and that's known as electron flow, but at the same time, there is the flow of positive charge, which is in the opposite direction. That's referred to as conventional flow. So a lot of people start arguments over these two flows as if one is which one's the real one, in other words, or like and the answer is they both are. They're both happening simultaneously in opposite directions. So it's not that there's one that's more real than the other or better than the other one. The people that debate that, I think, are probably stuck on the fact that the electron flow involves the particle known as the electron, so they like attaching themselves to an actual thing, particle, I guess, with mass that's moving. But the migration of positive charge is just as real in the other direction. And so we'll illustrate all this for you. And the truth is, I mean, not that I would ever pick a fight over any of this. It's not worth it, but the lunchroom debates that go on sometimes between people who want to pick a side, it's not, don't pick a side. They both happen. But the one I think that there's a tendency, the history of it is true. I think in the early goings of electricity, trying to figure, people that were studying it and trying to figure out what it is, they initially attached a positive charge to the moving particle, and then we found out no, the moving particle is actually the negative charge. So some of these people want to bring that up. You can read about it. It's not so important. What was I going to say about that? Well, the truth is, particle or not, the theoretical physicists would even weigh in on the fact that we don't really even know what an electron is. So there's that. Anyway, so that's, I'm digressing a good bit, but you'll probably run into it at some point. But let's map it out for you, what this is all about, and I hope you'll walk away from this video and realize it's silly to try to win an argument between the two when both are happening. So here we go. All right, let's see. We've got maybe a schematic symbol that will represent a voltage source, and it's a long line, a short line, long line, short line. The long line side is the positive side, and the short line is the negative side. So this would be the schematic symbol for a voltage source, and then you kind of can see internally what would be happening is, like in the case of a battery, there'd be a chemical reaction that's stripping away electrons from here and moving them down to this side. Internally, this would be happening. So what you're going to have is you're going to have the electrons that are getting pulled from this side down to this side, and so you're going to have an excess of electrons, here. In the case of a battery, it would be done with a chemical reaction, and you'll have fewer electrons up here. By the way, at the positive terminal, when those electrons leave, they leave behind what's known as a hole. There's a space there. And that is, in fact, the reason that you have a positive charge here at this terminal, is because when you have an electron that was pulled away from an atom, that atom now has more protons than electrons, and therefore has a positive charge. So these holes represent positively charged atoms. due to the fact that they're missing an electron. Remember, a neutral atom has an equal number of electrons and protons. And if you start taking electrons away, obviously you're going to get positive charge developed here, represented by holes where electrons used to be. And now there's an area of positive charge there. So the solid circles will represent our electrons, and the open circles will be the holes where an electron was. So this is what's going on in a voltage source. You're creating this imbalance that we know as voltage. Now, if you create a path, let's do it with like a wire, a conductor, some type of metal. Works well for metal works well as a conductor, and we'll talk about why down the road in another video. But yeah, so we have our metal wire. So let's look at what's going to happen once you provide a path. Then you'll get current, right? Things will be able to move. That imbalance with extra electrons. The extra electrons are going to want to go around like this, right? In that direction back to here. So that will be the electron flow. So this is the flow of the electrons, otherwise known as electron flow. So that's one type of current. But positive charge will also be flowing the opposite direction. And let's try to show you how that happens, okay? Because I think sometimes it's a little harder to see that because the spaces, the holes, they will migrate. The positive charge migrates, but let's show you how. First thing we have to establish to show you how the conventional flow is happening. The first thing we have to establish is this wire is not like an empty pipe. It is full of electrons, okay? So it's very important when you're trying to understand what's happening with electrical current, voltage, the path. You have to see the path as full. Even in the water analogy, it would be like not an empty pipe, but it would be a pipe that's already full of water. And let me finish. I should try to finish this up here. So that's important for a couple reasons. To understand that the wire you connect is full of electrons. Because what's gonna happen is for an electron current to flow, it's not like an electron's gonna leave here and then just sort of rattle down through an empty pipe type thing and eventually get to here. No, think of it if they were like marbles. Then think if this marble comes here, all these marbles are next to each other. If I could draw them all tight against each other, what I'm trying to sort of portray or get into your mind is that when an electron moves here, this electron will move simultaneously. They all move together. So as soon as you push here, there will be movement here because this is all along here. This is all full of electrons. Movement of an electron at this point here is simultaneous with movement of this electron here. They'll all push in. So I don't know. Hopefully that helps you. Because in reality, when you're doing circuits and stuff, you don't have to wait for current to arrive. Any current movement in the wire happens all throughout the wire. Okay. So hopefully that helps you. I hope I described that well. But think of it as a full pipe or full of marbles, whatever helps. Okay, so let's see if we can establish, so that's the electron flow. Let's see if we can establish this conventional flow, and that is what we'll be using. And there are probably about 3 reasons I can think of why conventional flow is preferred when you're doing circuit analysis, when you're looking at schematic symbols. So our book is all conventional flow, and again, it doesn't matter which one you study, because they both exist and they're just opposite. But conventional flow has some really good perks for using it, and we'll try to point those out as the year goes on. Okay, here's how conventional flow happens. Let's say, if this isn't too messy now, but let's say, let's see what happens when this hole is here at the positive terminal, and as soon as you connect a conductor, a wire, you'll see that this electron can move right into that hole right there. Maybe I'll change color here. Well, I don't know, I guess I can leave it. But do you see that this negatively charged electron here will be attracted to this positive charged area? And in fact, it'll drop right into that spot to fill that hole that was left by the electron that was pulled away down to here. So an electron will drop in there. Now watch what happens. This electron here leaves behind a hole. And then this electron jumps in there, right? Okay, jumps in there, but it leaves behind a hole. And this electron jumps in there to fill that, because again, opposite charges attract, and now there's a hole here. And this electron jumps into there, right? And now there's a hole there, and so on. Do you see that the positive charge here is moving? It is. It was here. It was here. Then it was here. Then it was here. Now it's here. Soon it'll be here, so on. So, okay. So this is a real thing, and positive charge flows in this direction, and we know that as conventional flow. I think it gets the name conventional because, like I said, in the early days of experimentation, they had to pick positive, negative. They had this notion that yes, it is opposite charges, but and they just picked one as the moving thing. So, but they both are real. They both both are happening simultaneously. So I hope that helps clear up any debate as to which is the real one. They're both real. Like I said, we'll be using conventional flow, and that is the flow of positive charge, and that's quite a mess, that drawing. So if I can do it maybe a little cleaned up here, and we'll just show you, let's say we have a simple little circuit here. Oh, we could just take a little light bulb here, right? And there's the symbol for a light bulb. And what this means is, for us, for our studies, our voltage source is looking, the wide line is the positive side, the short line is the negative side. So that's our voltage source, and for all of our studies, it's going to be current that runs in this direction, like that. The current always will be leaving the positive side. Yeah, it'll be leaving here and going around to the negative side of the power supply. So that's the conventional current that we'll be using, that direction for current. Because the thing is, you don't want to go dancing back and forth and constantly reminding yourself, well, if the positive charge is going this way, electrons are going that way. Pick one and stick with it for your studies. That's the way to do it. Otherwise, you'll drive yourself crazy. Looking at the mirror image constantly isn't a good idea. So you always want to pick one to do all your studies with, and then know that the other one's happening. Okay.